So now let's talk about motion analysis. Motion basically is one of the most important research topics in computer vision, but there are actually several very important issues that needs to be investigated in different things. For example, for in 2D and 3D motion representation, and how to calculate this 2D motion, and from 2D motion how we can infer 3D motion. So basically the problem is based on the structure and the motion. So we already saw, the structure of motion. So now, for using this knowledge, we are going to try to use this knowledge to be able to come up with an actual understanding of how we can represent particular motion. So now, the critical problem for this is how to construct correspondences. As we saw before, when you have different feature matching, sometimes the correspondences are not, correct. So how do we actually construct the good correspondences of all these different features? Okay, so these correspondences can be in many different forms. Right now we saw for point correspondences, but there can also be different line correspondences, curve correspondences, region correspondences. So it can be like different types of correspondences. So this is just the way we can actually structure the problem. So one way to solve this is well, there are actually two ways to solve it. One of them is the dense approach. This one is by trying to build a correspondence pixel by pixel, but this is actually very time consuming and very complex. It takes a lot of computation and time. And the other one is it's called sparse or feature based approach, which is the one that we were talking about in the previous slides. Basically, we're trying to find the matching or associate different image features based on their similarities or their different properties. So for example, we have in this case the problem definition of how we can find a particular motion is that let's say we have two or more particular frames. Let's say we're recording a video at different frames per second, and then we can have the video or the images for these two particular frames. So we want to calculate the displacement field, between two consecutive frames. So this is actually what is defined as the optical flow, which is the displacement field, which is the actual direction of particular features in two consecutive frames. So basically, we have a particular initial image. In this case, we have x, y at a particular time t, and we want to find the optical flow from this image to another image in which the time we have a +1 transition. Now we cannot really observe the motion field directly into a particular image, because we don't know exactly the projection or where these points move in 3D space. Okay, so we can only observe these image points in a 2D space scenario, and the only thing that we can say is that the image point moves from one point to another, from one particular place to another. But in this case, this is how we can indicate the optical flow for these particular points into the image. So for example, we have this initial original image, and then we have other images based on the consecutive frame in this case. So from here we can calculate these particular vectors, okay, for the correspond to the same correspondence of the 2 points in the different frames. So these are called the velocity vectors, and let's see how we can actually calculate these velocity vectors. So here, given two subsequent frames, two consecutive frames, we calculate these velocity vectors, but we need to assume something very, very important. We need to assume that there is a brightness consistency, okay, which is the projection of the same point, okay, the same region of the image that looks very similar to the next frame, okay. So if there's a very drastic change in the scene, then we cannot calculate the actual vector. So we need to assume that we have a very similar brightness in the particular points that we're trying to calculate. So for example, this is an example of brightness consistency. Okay, we are calculating the brightness of the small region, and we are assuming that it will stay constant in the next frame. So the way we calculate is that initially we have a particular image with the parameter a particular point. For example, we have x, y, and time and t. Okay, and the velocity vector basically is given by the derivative of the initial position over time, right? So for this we have the velocity of the image pixel based on the on on the on this particular equation, as you can see here. Okay, but here right now we are assuming the brightness consistency during the time transition. Okay, and this brightness changes smoothly, as we were mentioning before. Okay, because we are assuming there's no drastic change, so it needs to change very gentle, very smoothly. And then by using this we can easily transform this equation into a Taylor series approximation. I hope you remember your calculus. And why we can do this? Because we can then define just as a representation of the vector and the partial derivative of the image position and the time. Okay, which is defined as this is basically equal to 0. So the actual equation for optical flow is this constraint equation that we can actually define this image distance velocity plus the actual partial derivative, which equals to 0. So this is called this equation contains a particular gradient, okay, which is defined by a particular pixel. So this is just how we can actually define this particular velocity. So some of the extraction for motion, okay, some of the applications are, for example, for robot navigation, because we can know the direction of where the images are moving. Okay, also for surveillance and tracking, action recognition, okay, and also for other different applications for stereo reconstruction and also medical image registration. But let's see some of the examples. As we can see here, there are many vectors that are coming from different regions of the image, and these vectors are based on the actual computation of the matching of two features of the consecutive frames, as you can see here. This is for navigation, for example. We can know where how a particular object is moving based on the vectors of the optical flow that we can calculate of two consecutive frames. And finally, this is another example of how we can define the motion of a particular object, and we can use it for purposes such as like a human interface interaction. So this is all that we have for this lecture. If you have any questions, please send an email, and I'm gonna try to answer your questions. So at the end of this lecture, we're gonna have a quiz. So good luck in the quiz. Thank you.